After we develop the model, we need to validate the model. This is model validation. The model validation is very similar to model calibration. This is because both of them need to use measured data, the data from the real process or the data from the experiments. However, model validation is different from the model calibration. This is because the model validation should use independently measured data set. This data set is also called validation data. The validation data should be different from the data used for model calibration. When we develop the model, we use a set of data. However, when we validate the model, we should use different set of data. In the model validation, we can compare the predicted outputs from the model with the results from the measured data. That should be y predict compared with y from the experiment. We can also compare the estimated parameters of the model based on the validation data to the estimated parameters based on the calibration data. That means from the calibration data, we can get the values of the parameter, and using the model validation data, we can also get the values of the parameter. Then we can compare the values of these two parameters and then to see the difference. The smaller the difference, the better the prediction. We also use example 9.1 to show you how to validate the model we developed for reaction rate constant. We have this model for reaction rate constant. This is the calibration data that are used to develop this reaction rate model. For model validation, we need to create another set of data. This data is called validation data. You can see the validation data is completely different from the calibration data. And then, based on the validation data, we can get the predicted value for reaction rate constant. Then we can use the parity plot to show the reaction rate constant measured from the validation data and the reaction rate constant predicted from the model. And then you can see all data points are on the diagonal. That means all data points are on the line y is equal to x. And then we can conclude the model predicts very well on the model validation data. Next, we discuss how to use the empirical modeling approach to develop a mathematical model. This modeling approach is also called black box modeling approach. As we introduced in topic 3, when we don't know anything about the process, then we should use the empirical modeling approach. This modeling approach is completely based on the input and output data. Based on the input and output data, we can observe some trend of the input and output data, and then we can come up with some model. After we come up with some kind of model, then we need to determine the parameters in the model. As we mentioned in topic 3, the parameters in the black box modeling approach usually have no physical meaning. In this empirical modeling approach, we also need to identify the set of independent variables that have great effect on the performance of the process. For this example, If we don't know the reaction kinetics and we don't have much knowledge about this process, like fermentation process, then how can we develop reaction kinetics for this reaction using the empirical modeling approach? There are several steps for the empirical modeling approach. First, we identify the set of independent variables. The independent variables are usually flow rate, temperature, pressure, composition, concentration. We list all possible independent variables. Then we can use factorial experimental design to measure the data from the real process or from the experiments. Here, we don't introduce what is a factorial experiment design and how it works. If you have an interest, you can read the chapter 2.4 of the book Optimization of Chemical Processes. From those data, then we can identify which variable has greater effect on the performance of the system and which variable has no effect on the performance of the process. Then we select those important independent variables and then observe the trend of the input and output data. Then we can draw figures to show the process performance indicator Y with those important independent variables. We can observe the trend of the curve and come up with some type of models based on the observation of the measured data. If we can see the trend is like a linear, then we can come up with a linear function. If the trend is like a polynomial, then we can come up with a polynomial function. If the trend is like exponential, then we can come up with the exponential function. Then we use the model calibration to obtain the values of the model parameters. And then we use another set of data to validate the model that is developed. The model calibration and validation is very similar as the gray box modeling we have discussed in this topic. There are several types of models that can be used for the empirical modeling approach. This is a linear model, then this is a projectical model, this is a exponential model, and then this is a logarithmical model, this is a polynomial model, and other types of models. Okay, let's use another example, 9.2, to show you how to use the empirical modeling approach to develop the mathematical model. In this example, we have reaction use A to produce B, and now we want to develop reaction rate model. We don't have any knowledge about this reaction. Following the steps for the empirical modeling approach we have discussed, first we need to identify the key important independent variables in the reaction that will affect the reaction rate, right? We first list all possible independent variables like flow rate, like concentration, like temperature, like pressure, that could have effect on the reaction rate. Then we use the factorial experiment design to measure data. After we have the data, then we do some analysis of the data to identify which independent variable has great effect on the reaction rate and which independent variable has no effect on the reaction rate. Based on the analysis, we identify the concentration of A has great effect on the reaction rate. Then we have the data with different concentration with different reaction rate, and then we can draw the data point between the reaction rate and the concentration, you can see the point with square shape. Then we can observe the trend of these data points. Then we can see it seems like a polynomial curve. So then we can come up with a polynomial model for this reaction rate. Then we have Ra is equal to A plus B times Ca plus C times Ca squared plus D times Ca cubed. If you think the trend is like exponential, then you can also come up with exponential model. Then we can do the parameter estimation to get the values of the parameters A, B, C, and D in the model. This is an optimization problem we can construct. And solving this optimization problem, we can get the value for the parameter A, B, C, and D in the model. And then finally, we get this reaction rate model for this example. In this polynomial model, we assume the degree is 3. We can also try other degrees like 2, 4, 5, and so on. For each degree, we can get the values of the loss function. We can then select the best polynomial model with the minimum loss function value. We use the parity plot to evaluate the quality of the estimation. From this parity plot, we can see all data points have a small scatter near the diagonal. That means all data points are very close to the line y is equal to x. That means the model predicts the data very well. We also use residual plot to see the systematical deviation. From this residual plot, we can see it shows a fairly random pattern. That means there is no systematical deviation between the reaction rate, residual, and the concentration of A. That means the model predicts very well. We create another set of data with different concentration and corresponding reaction rate. And then we do the model validation. From this model validation, we can see the model also predicts the validation data very well. If we compare the empirical model with the model developed by using the theoretical approach, then we can see the difference between them. The red line is the reaction rate from the theoretical model. The blue dashed line shows the reaction rate from the empirical model we developed. Then you can see in the range of the concentration from 0.2 to 0.8 performs exactly same as the model from the theoretical approach. However, if the concentration is smaller than 0.2 or the concentration is greater than 0.8, then you can see there is a large difference of the reaction rate predicted by the empirical model and the theoretical model. The empirical model does not predict very well, so the empirical model cannot be used for extrapolation. Okay, in this topic, we mainly introduce how to develop the mathematical models using the semi-empirical modeling approach and the empirical modeling approach. When we know something about the process and we don't know something about the process, then we should use the semi-empirical modeling approach to develop the mathematical model. However, when we poorly understand the process, then we should use the empirical modeling approach to develop the mathematical model. The model parameters in the semi-empirical modeling approach usually have physical meanings. However, they usually have no physical meanings in the empirical modeling approach. We also mentioned when we validate a model, the data set should be different from the data set that is used to develop the mathematical model. This is very important. Hope you can fully understand this topic. Then we finish all topics for part 1, problem formulation. Hope you enjoy these 9 topics and know how to develop mathematical formulations for a given process synthesis and design problem. In part 2, you will learn how to solve the mathematical formulations you have developed, and you will learn different optimization algorithms. Thank you very much. See you next time.